the first speaker. Ekel Ben-Ahmed is, I don't remember if you are PhD student.
No.
No, associate professor.
I'm at the conference.
Oui, associate professor, sorry. Associate professor in University Picardie Jules Verne, in the north of France. And Ekel will talk about Darcy mixed convection of binary liquid mixtures.
Thank you. Hello, everybody. So that I'll speak about macroscopic motion of mixtures of liquids in porous media and how to extract application to petroleum field. So that is enhanced oil recovery. After some period of exploitation, the pressure in the reservoir falls. So that we have to inject something, water for example, to elevate pressure. So we have an injection zone, a miscible zone, and here the object of study, the reservoir of oil of hydrocarbons. Here we have an horizontal gradient of pressure, a vertical gradient of temperature, and a mixture of hydrocarbons. So the idealized situation is a parallelepipedic model with a through flow, a velocity at the entry, velocity at the exit of the duct, and an adverse gradient of temperature. Here we have the hot temperature, the cold temperature. We assume that there is equilibrium of temperature on the vertical walls so that the flux is null. I know that you are all fluent in mathematics, so that I'll speak about physics. In order to streamline oil exploration and optimize development scenarios, pumping technique, position, duration of exploitation, etc., companies seek to know before and during the production the local composition of hydrocarbons in oil fields. So numerical simulations and theoretical tools seems to be necessary to estimate overall the composition of the reservoir. To date, all oil companies are continuously working to improve their simulation models. For example, Total Company works to have a software able to simulating correctly the macroscopic dynamics of multi-constituent fluid in porous media. It is also estimated that Soret effect, ignored to date by several of these models, may, on geological times, have a significant influence on the distribution of hydrocarbons. A little word about gradient vertical temperature. Some reference gives 18 degrees Kelvin per kilometer of height, and some reference gives about 13 degrees Kelvin on kilometer. But geothermal gradient results of heat rising from the Earth mantle, it varies strongly at different regions of the globe. So what happens when heating a liquid from the bottom? Liquid would to evacuate energy. At first stage, energy is evacuated by conduction. And when the amount of energy evacuated by conduction, the amount of energy is greater that it can be evacuated by conduction, the liquid begin to move. This is what we call convection. If 3D cavity is very little, we have only 2D structures. But if we have cavities with great aspect ratio on the depth and on the length, here we see a numerical simulation. It seems to be cow, but there is not a cow. Look, for example, this view top. It's a very organized structure. We can almost write exact equation of the results. we have sources of outgoing matter and sinks of ingoing matter. And we have oblique rolls of convection. This is natural convection. Here we show the isosurface of W speed. Clearly we have oblique structure of convection. Here we isolate one structure. The important information is this motion is stationary for natural convection, and for one liquid, one pure liquid, the convection is stationary. Let's write the equation. The equations of motion of one liquid in porous media is the Navier-Stokes equation. This problem is very simple. But in the reality, there is more than one component. We have two or several components. So that we have to add an equation, the space equation, concentration equation. And we have two new terms, two new source terms, and the Laplacian of T. What's N? It's the buoyancy rate. It relates concentration of one of the components and the coefficient of expansion of the liquids. And the Laplacian of T in the equation of concentration is the Soret effect. The Soret effect is a natural effect. Here we see a fluid in equilibrium. This matter and this matter needs different amount energy to expand. So with the same amount of energy, the expansion is not the same. And then natural separation occurs when gradient of temperature is applied. So the Soret effect is a concentration gradient induced by a thermal gradient. Its action is not very speed, but on geological times it can induce an interesting separation of species in oil jasmine. Soret effect is systematic. Here we will speak about the importance of Soret effect. It is systematically present once a fluid mixture is subjected to temperature gradient, and that gravity is present or not. But since the presence of gravity, temperature gradient produces a convective motion, which tends to mix the fluid and makes the Soret effect unobservable directly. So experience in microgravity or in space seem to be very useful to determine the Soret effect. The importance of stationary convection. Stationary convection conserves separation obtained on geologic periods, so that we have to study the stability of convective solution. Here we show the solution for stationary convection. Here is the concentration gradient. We see that concentration is the liquids are very separated, but here in oscillatory case the fluids are very mixed. So that we can't, so that the exploitation of the reservoir of hydrocarbon will be more difficult. Technical approach to solve the problem of Darcy-Navier-Stokes equation coupled with concentration and temperature. We have two approaches. Analytical approach, linear stability analysis. To find the threshold of different regimes, we use normal Fourier modes, and in some zones we use weakly nonlinear analysis, essentially amplitude equations and Landau equation. To solve the nonlinear complete system of equation, we use finite volume multigrid and finite element and finite difference to solve dispersion equations and Landau equation. So this numerical method to solve the dispersion equation issued of linear stability on the weakly nonlinear stability systems. The main result of the first part, here we have the N, the buoyancy rate. It explains the separation between components. So when N is positive, it means that heavy components go down and the other components go to the top. It's a natural configuration and a stable configuration. But when N is negative, it means that heavy components go to the upper side, so that it is not the stable configuration. Here we have the rest state. There is no motion of the fluid. Rayleigh number is a dimensionless number which explains the amount of energy necessary to make convection. Here we have the rest states. There is no motion. Here we have stationary convection, but here we have a Hopf bifurcation. So that oscillatory convection. This point belongs to the two curves. So we have very rich dynamics at this zone. At this zone we use weakly nonlinear theory and numerical simulation to see the behavior of the liquid. To remember, we have an horizontal gradient of pressure, so that we have a filtrating flow on the studied zone. So we don't have natural convection, but we have mixed convection. And this diagram is given for natural convection. So what happens when we apply the horizontal gradient of pressure? A little comparison. In natural convection, wave number on x and y direction are not null. All linear combination of kx and ky wave numbers are solution of the problem. Numerical solution gives preference to diagonal rolls, as we have seen. In mixed convection, when we apply the horizontal gradient of pressure, through flow induces other kind of bifurcation. We have convective instability and absolute instability. What is convective instability? Convective instability is when the instability is born. The filtrating flow takes this instability ad infinitum. So the instability is not a real instability, it's just a perturbation, a noise. But absolute instability is instability that can be amplified locally. So it's instability which determines the real motion of the liquid. The problem, we have transversal rolls and longitudinal rolls. But what's transversal rolls? Transversal rolls are rolls with kx, the wave number in the x direction not null, but ky are null. The transversal rolls makes traveling waves and are absolutely unstable before longitudinal rolls. So here we have the x direction. When we hit, transversal rolls makes the liquid move, and the separation of constituent is not very good. The liquids are very mixed. The traveling waves can go with the through flow or against the through flow. But longitudinal rolls are stationary structure. Look at the concentration here. The concentration of the different components of hydrocarbons are stable, so that we can make some things to extract petrol at these zones. Here are some details of calculus of normal modes to find the absolute instabilities. The main result of this study. So, Rayleigh number is a number related to heating It's proportional to the adverse gradient of temperature. When heating, the convection, when Rayleigh number is greater, that means that the gradient of temperature is great. But we can't control the gradient of temperature in oil judgment. It's a gradient imposed by geological data. So we can control only the pressure. Here we give the zones with traveling waves, transverse rolls, and zones with stationary longitudinal rolls. We are interested by this zone because stationary convection gives the most separated case. The other parameter to control the rolls, the convection rolls, is the Reynolds number. The Reynolds number is proportional to velocity, and velocity of through flow is proportional to the gradient, the horizontal gradient of pressure. So, when we put a very low pressure, oscillatory structure seems to appear at first, but when the pressure is more higher, stationary structure will appear, and we are interested by this zone. So we have to put a higher pressure to have stationary structure. But a very high pressure gives another mode of convection, terminus-listing waves. It's another oscillatory stage. So we understand that we have an optimum interval of pressure to have stationary structure, and so that to have the best separation between components of the hydrocarbons. To conclude, stationary convection conserves separation obtained on geological periods. The stability study of convective solutions shows that transversal rolls are oscillatory, but longitudinal rolls are stationary. They conserve separation. The stability of absolute solutions shows that transverse rolls are the lower unstable mode. They appear before longitudinal rolls, before the stationary state. The longitudinal rolls are produced with a critical minimum of pressure, so we can control concentration by controlling pumping. And I thank you for your attention.
We have time for one or two questions, please.
In your simulation,
Oui.
you are in a monophasic
No.
flow.
No.
So you have two-phase flow.
Monophasic flow. Yeah. Monophasic flow.
So you mean only oil in your layer?
Yeah.
All right.
Only liquids on my layer, with higher Prandtl number and with higher Lewis number.
One liquid.
No, not one liquid. A mixture of miscible liquids.
Of visible liquid.
Yeah. But we control these miscible liquids by the concentration.
Okay. And do you need a minimum temperature threshold?
Yeah.
Yes.
Yes.
In order of magnitude to induce that?
For porous measure, the temperature depends. I will show you the expression of Rayleigh number. So the Rayleigh number is a dimensionless number which quantifies the amount of energy necessary to create motion in liquids. It relates gravity, expansion coefficient, permeability, the height of the cavity, viscosity, and thermal capacity. And here we have the gradient of temperature on the two layers. So in a Petron structure, we control anything on the Rayleigh number because gravity is gravity. Here, these are the physical properties of the liquid, and the delta T is imposed by a geological state. But what we can control the pressure of the convection of water. So the critical number, Rayleigh number to have convection for Darcy media, for example, is about 14. For
idea of the velocity of the wall.
yeah, we can calculate velocity, concentration, wave numbers.
How much? Meters per second.
Meter per second. It's a very slow second. Here I made calculus with dimensionless parameters, and in order to some centimeter per second.
By the way, okay, go ahead.
Thank you. It was not completely clear for me. In which case do you consider Darcy? In which case do you consider Navier-Stokes? And that's the same kind of instability?
Yeah. Here we have, look, this equation is the momentum equation. It's the Navier-Stokes equation combined of the Darcy with the Darcy model of filtrating flow. Generally, in the Navier-Stokes equation, we have a term of the tensor of stress, which quantifies the shear stress, le cisaillement. In Darcy medial, this tensor is negligible, but we have the Darcy number here. Here we have the filtrating flow, so that we have a combined equation between momentum and Darcy model.
What did you say? It's Navier-Stokes equation, it's Darcy equation, coupled with temperature and C, and concentration. You
Yeah.
don't have the non-steady term and you don't have the non-linear term, no?
Yeah, we have nonlinear terms. Here we have nonlinear terms. Here we have nonlinear terms. Here we have nonlinear terms. The equations are coupled because the temperature induces a variation on velocity. Velocity induces a variation on temperature. The concentration induces variation on velocity. Velocity induces variation on concentration and temperature. It's a system of 7 equations, which are very, very coupled and and strongly nonlinear.
No, I was looking for the non-linear term, convective term involving the velocity. Okay, it's coupled with temperature.
I can show you the details.
I stop you. I am greatly interested. We have to talk because this could explain some geophysical phenomena, micro earthquakes, which are periodic in my native city. So this. Okay, so.